Before we get into the physics, let's talk about what exactly a zipline is. A zipline is a rope suspended at a high tension between a higher point and a lower point that people slide down. The first ziplines were used by ancient South American cultures to move from tree to tree above the rainforest undergrowth. Around the same time, people in the Himalayas used ropes to deliver supplies from village to village. Ziplines were first used for recreation by steeple repairmen in 17th century England, who flew down in front of large crowds on ropes that were often a bit too steep. Ziplines with a slope of 4 to 8% gradient are ideal for an exciting but safe ride. As the slope becomes steeper than 8%, the normal force between the rope and your pulley acts less and less to reduce acceleration due to gravity. People pay to go on ziplines because they're fast. Ziplines are not vectors, since they are not completely straight, but they are just about the shortest scalar humans can take between two elevated points. A person spends about 2/3 of a zipline ride accelerating in the positive direction from rest to top speed, anywhere between 50 and 150 kilometers per hour, before accelerating in the negative direction back to rest on the end platform. These motion graphs show that because the velocity change is the same amount between events 2 and 3 as between events 1 and 2, but over a shorter distance, the negative acceleration must have a greater magnitude than the positive acceleration. But why are you speeding up and slowing down? It's not like anyone's forcing you to do it. But wait, something is forcing you to do it. Forces. Ziplining with your bare hands would be painful and slow. That's why zipliners hold onto a pulley with grooved wheels that rest on the rope, which reduces the coefficient of friction between the zipliner and the rope. Pulleys also include a brake so that the zipliner can increase friction to slow down. By splitting the force of gravity into its component parts, we can see that there is an unbalanced force about 10 degrees south of east that makes the zipliner speed up. Once the forces of gravity and friction are going in the same direction, there is a stronger unbalanced force that slows the zipliner down. Now, our good friend Isaac knew a ton, and through his experiments, he wrote down some nifty laws that we can apply to ziplines. Newton's first law. According to Newton's first law, this wild child will continue to drift along this zipline, growing old without her friends and family, unless a force acts on her to slow her down. Luckily, on ziplines, the forces of friction and gravity act on riders to return them to rest. Newton's second law. This law states that the mass of an object does not affect its acceleration during free fall. However, because heavier objects make a zipline sag lower, they lose more gravitational energy, which is converted into more kinetic energy, at least, if the rope holds up. Newton's third law.
If there is no force acting against you along your zipline ride, you would hit the end mat with a force that is equivalent to 32 punches in the face.
This really hurts because it's a high frequency. Energy. This guy is confused. The law of conservation of energy states that energy can't be created or destroyed. So why do you end every zipline below where you started? Where did the gravitational energy go? The answer is that some energy is lost to the rope as thermal energy, some as sound energy, and some is also lost because of air resistance. Between events 1 and 3, the zipline and the air do negative work on the zipliner, so the sum of gravitational and kinetic energy is gradually decreasing. Hopefully all this talk about energy has given you the energy to go do some ziplining. Thanks for watching, guys.